record. Okay, we just finished up section 6.1 in chapter 6, counting method and the pigeonhole principles. Here in this web address, we have the lecture note, and we finished up section 6.1 basic principles. We now start the section 6.2 permutations and combinations. Okay, here. A permutation of n distinct element xi's is an ordering of the n elements x from x1 to xn, and that's the permutation. How many ways of choosing of the ordering, arranging, the listing of those an element with an order. Okay, example 2.2. There are 6 permutations of 3 elements A, B, and C. Then it has 6 permutations, which is ABC, ACB, CBA. Like what? For example, yeah, we can, if we choose, we have one choices for the first position, which is 3. Then we have the 2 choices for the second one, and we have only 1 choice left. So 3 times 2 is 1. We have a 6. This is the listing, ordering of 3 elements with the order 6, 3 factorials. Okay, if n is equal to 4, then we have 4 choice, 3 choice, 2 choice, and 1 choice. And this is kind of the Python-based Sage code for permutations. We need to find the permutations and ordering. For example, if we go inside here, then we will see the code. For example, here is a permutations and combinations. Here is n permutations. Here is a permutations. We see the multiplication principles. Now, permutation of n element can be constructed in n successive steps. Select the first element, which has one n choices. Then select the second element, which has n-1 choices. Then find the third element, which has n-2 choices, because 2 elements from n was already taken. So it's going to be n factorial permutations of an element. So by the multiplication principles, this can be done in here. The element, suppose you have a 3 element, then arrangement of these 3 elements, and find those permutations. Then count the cardinality of them. Then we have arrangement of the set of length 3, which is this. There are 6 ways of that, which is same as the 3 factorials. Suppose we have 4 element, 4 element like the, and arrangement 4. Then count of it. Then we ABCD. Then we have 24 different ways of choosing. The switch is same as 4 factorials. Okay, that can be done. So number of permutations is n factorials that can be found in here. 치환의 숫자 n factorials. Next example, 4 tokens to permute. Then how many permutations of letters A, B, C, D, E, F contains the substring DEF. To guarantee the presence of the pattern DEF in the substring, these three letters must be kept together in this order, like this. So the remaining letters are A, B, C. So we have basically 4 blocks to be arranged. So you can think of constructing permutations of the letters that the pattern DF by performing as 1. So we have how many? We have 4 different objects to be arranged. So we have basically 4 factorials. It's the numbers. Okay, so actually this is the same one. So how many permutations of letters A, B, C, D, E, F contain the letters D, E, F together in any order? Oh, then first, the select and ordering of letters D, E, F, which is 3 factorial. So these 3 letters can be rearranged in 6 different ways. Then next, the letters should be together. So we have 4 letters for object to have the permutations, which is 4 factorials. Then by the multiplication principle, we have 24 times the ordering of this DEF, which is 6. And so multiply 6 on 24, which gives us 144. Different ways of permutations for the letters A, B, C, D, E, F contains the letter D, F together in any orders. Next. Okay. In how many ways can 6 persons be seated around a circular table? So we have 6 persons. Okay. But if we fix one seat, say A is fixed, then find the seat for remaining 5 persons. Okay. So this is 5 factorial, which is 120 permutations of 5 elements. So basically there are 120 ways that 6 persons can be seated around a circular table, because they can be sitting in anywhere. So fix one and then order the remaining. So there are n-1 factorial ways that n persons can be seated around a circular table, which means the only matters who sit next to the others. In that case, we just divide n factorial and divide by n, because there's no position fixed as the first or second or others. So it's divided by n of n factorial, which gives us n-1 factorial. Next, R permutations of n distinct elements. An R permutation of n distinct elements xi's is an ordering of an R element subset of xi's. So the number of R permutations of a set of n distinct elements is denoted by P's of n and R. So R permutation of n distinct element. Okay, we write it in that way. Think about the next example, 2.9. Ordering picks lead theorem 2.10. Example of 2 permutations of ABC are, choose 2 out of ABC. So A gives AB, AC, and BA. You know, 2 permutations AB, BA, BC, CA. Huh? Yes, that's right. Yeah, these are just one example of some examples of 2 permutations of ABC. Yeah, we can choose these 2 permutations out of these 3. There are more 2 permutations. Okay, this is one example. If R is equal to n in definition 6.2.8, then we obtain an ordering of all n element. Okay, so thus an R n permutation of n element is what we previously called simply a permutation. So this is a generalization of the just n permutation. Okay, so and P of n is an n factorial, and the number P of n and R of R permutations of an element set when R is less than n may be derived as in the proof of theorem 6.2.3. Okay. And next theorems. Yeah. This is the number of n permutation of a set of n distinct objects is P of n and R, which is and we choose the first one has a choice of n because we choose any one from n object, and then the next one should have n minus 1 choice because one is already taken, and the third one we have n minus 2 choice because 2 are already taken. And then the R's term has n minus R plus 1 choice to be chosen. Then product of all this by the multiplication rule gives us P of n and R. So this can be rewrite as n factorial over n minus R factorial. So this is R permutation of from n. Okay, this is what I said. You have the first one has n choices, second n minus 2 choices. The R minus first element is selected. So R's element is in n minus R plus 1 ways. So by the multiplication principle, product of this gives us this. So this P of n and R in terms of factorial can be written as this. You see. So P of 3, 2 is 3 times 2 times 1, which is 6. According to theorem 2.10, then the number of 2 permutations of X is 3 times 2.1, which is 6. So we have 6 2 permutations of 3 object ABC. And next, in how many ways can select a chairperson, vice chairperson, and secretary and treasurer from a group of 10 persons? Okay, we are choosing 4 member committee. So the ordering picks uniquely is a chairperson. So we choose the chairperson first. How many ways? 10 ways. Next, we choose a vice chairperson from 9 persons left, and then choose a secretary, which from 8 persons left, and then choose the last one, which is the treasurer from the remaining 7. So we have product of these 4 numbers, which is 5040. This is also same as 10 factorial over 10 minus 4, which is R here. Factorial, which gives the same number. And read example 2.14. Basically, this section 6.1 and 6.2 are the ones that you have studied in high school years. Definition 2.15. Given a set X containing n distinct elements, an R combination of X is an unordered selection of R element of X. That means an R element subset of X. This is a combination. Before it was a permutations with order. Here without order for the combinations. The second B, The number of R combination of a set of n distinct elements is choose R from n. And choose R from n. Okay, so this can be written as n factorial over n minus r factorial times r factorial, because here there's no order, so just ignore order by multiplying r factorials. That gives us the whole number of r combinations out of a set of n distinct elements. Here's an example. The number of ways the 5 students can choose 3 of their group to talk with the chairperson is choose 3 out of 5. So this is number of 3 element of 5 from the 5 element. So see, so we choose 3 from 5. So see, choose 3 from 5. So 5 factorial over 5 minus 3 factorial times 3 factorial, which is 10. Okay, this can be also found with this code, Python-based Sage. Here we can check those code, the permutations, these cardinalities, and here in choose R. Here 5 choose 3. Factorial of 5 over factorial of 5 minus 3 times factorial of 3, which is 10. This gives you the same thing. So this computation also can be found with the binomial of 5 and 3. This is actually same as choose 3 out of 5 and choose R. Like this. Same thing. Next, the number of R combinations of a set of n distinct objects is and choose R, like this, which is same as P of n and R over R factorial, the same thing, which can be written as n factorial over n minus R factorial times R factorial. So this is what we did. This can be found. So this has a relationship. The permutation and combination has these relationships. Okay, so two permutation of A, B, C, D can be seen in these examples. And also this is another way of proving this n choose R, n factorial of n minus R factorial of R factorial. If the cardinality of x is equal to n, then R permutation of x is obtained by first selection R element from x and arranging them. So P of n and R is the n choose R, then the order given ordering of by n factorial. So this can be obtained by this, which is this. This gives us a theorem. If R is bigger than n, then there's no possible ways of choose that larger number. So actually, n choose R is equal to 0 if R is bigger, strictly bigger than n. Okay, next. In how many ways can we select a committee of 3 from a group of 10 distinct persons? Since a committee is an unordered group of people, the answer is this. 10 choose 3. 10 choose 3 from 10 choose 3 from the 10 distinct persons. So 10 choose 3. So 10 factorial, 10 minus 7, 3 factorial times 3 factorial, which gives us 120. Okay, next. In how many ways can we select a committee of two women and 3 men from a group of 5 distinct women and 6 distinct men? So choose 2 out of 5, which is 10. Choose 3 out of 6, which is 20 ways. So by multiplication, rule the total number of committees, possible committees is 10 times 20, which is 200. Next, how many? 8 byte strings contain exactly 4 ones. Okay, so 8-byte strings contain 4 ones. Uniquely is uniquely determined ones. We tell which bytes are ones. This can be done in A choose 4. We just choose 4 out of 4 ones to fill it out. It gives us a factorial over 4 factorial times 4 factorial, which is 70. There are 70 ways of it. Next, an ordinary deck of 52 cards consists of 4 suits, which is club, diamond, heart, and spade, of certain denomination each, from ace and 2, 3, 4 to the 10 and J, Q, and K. Then how many unordered 5-card poker hands selected from an ordinary 52-card deck are there? Simply choose 5 out of 52. So 52 choose 5. It can be written in this way, and that's the number. 2,598,960. And that's for 2, yeah, B. So just think about C case 2. How many poker hands contain 3 cards of one denomination and 2 cards of second denomination? Here, the hand contains 3 cards of one denomination and 2 cards of a second denomination can be constructed in 4 successive steps. Okay, select the first denomination and then select the second denomination, then select the 3 cards of the first denomination, then select the 2 cards of the second denomination. Okay, so if we really count, then first denomination can be chosen 13 ways. And having selected the first denomination, then we can choose the second denomination 12 ways. Then we can select 3 cards of the first denomination in 4 choose 3 ways. Then you can select 2 cards of second denomination in 4 choose 2 ways. So by the multiplication principle, the answer is 13 times 12 times 4 choose 3 times 4 choose 2, which is 3,044. Okay, next, how many roots are there from the lower left corner of n by n square grid to upper right corner if we are restricted to traveling only to the right or upward? Okay, for example, one such route is shown in 4x4 grid like this. Here we got right, up, up, right, right, up, like this. Okay, if R represent the string of right direction and U means strings of upward, then string can be obtained by an order of selecting n positions for the R's among the 2n positions in the string. Okay, 2n positions. Then filling the remaining position with U's. Then we have R's here. Then choose with the ups. Up will fill out the rest of them to make a pass from here to here. So this is exactly the same problem of choosing n out of 2n. So 2n choose n. Okay, possible route like this. This is the way from here to here by steps. So binary sequence, shortest path, then has a one-to-one correspondence. So 1 0 1 0 1 means 1 0 1 1 0 1. It gives us path from 0 0 to 2 3. And this step is up. If I is equal to 1, right? If AI is equal to 0. So the number of passes from 0 to AB is same as A plus B choose A, like 2n choose n. Yeah, same, it works. Example 2.23, n by n times n square grid, and how many roots are there from the lower left corner of n by n square grid to the upper right corner if we are restricted to traveling only to the right or upward. If we are allowed to touch and not go above diagonal lines from the lower left corner to the right upper corner. Okay. Okay, this is an interesting problem. So actually, the explanation can be found in here on Catalan number. This interesting number is called as a Catalan number. So you can have an explanations from here. Okay, I will give you a chance to go through it by yourself with these explanations. But so I will give a sketch of proof here. Okay, so now we can think a good root and bad root. A good root means a root that touches but does not go above the diagonal, stays in the bottom of the diagonal lines. And bad root is a root that goes above the diagonal like this. So we want to count the number of good roots. Gn denotes the number of good roots and Bn denotes the number of bad roots. Then addition of those two numbers will be the 2n choose n, which is all the possible number from here to here. Here, when we have n by n square. Then compute the number of bad roots in this figure. X point 2.5b. Then and here we can we now have n plus 1 by n minus 1 grid like this. N plus 1 and n minus 1. From the lower left corner to the upper right corner. We have from here to here, we have n plus 1 times n minus 1 roots. The number of bad roots is equal to the number of n plus 1 times n minus 1 roots. Using the bijection function on the set of bad roots in the set. Okay, here, given a bad root, find the first move that takes it above the diagonal. Replace each right move by up move and replace each up move by right move. Okay. Then this transformation can also be impacted by rotating the portion of the root following the first move above the diagonal above the dash line. So each bad root is an n plus 1 by n minus 1 root. Okay. Then with some more argument, we can show that function is 1, 2, and that function, our function is 1, 2, 1. So the function transforms distinct bad root to distinct n plus 1 times n minus 1 root. Same. So for the number of bad roots equals the number of n plus 1 times n minus 1 root. So this number, whose root is equal to same as the 2n choose n minus 1. From here to here, the root is same as addition of this 2n, and we choose n minus 1. The steps, then the the others will be followed. If you count this, then it is same as this. So we, from the whole possible paths minus bad roots, which is this, then we found this number by these simple computations. Okay. On this number has a great interest. And Catalan is a Belgian mathematician who defined the number called the Catalan number while considering the solution of the problem of dissecting a polygon into triangle by means of non-intersecting diagonals. And you can take a look on those. Mhm, mhm, mhm. This is a MAA talk on Catalan numbers. Mhm. And you can take a look. Mhm, mhm. This is one. Mhm. So you can take a look on it. And also this has the good explanation. Mhm. This is a basic motivation for finding Catalan number by Catalan. When you cut it, those are possible numbers. So you can take a look on those to understand these Catalan numbers. And this video shows the solution of the problem. It is dissecting a polygon into triangles by means of non-intersecting diagonals. And also, I have made the web page on Catalan numbers that may help you. And yeah, this is a formula for the Catalan numbers. And the Catalan numbers can be written as this as a series. This and Catalan number is has the theorem that we just showed can be rewritten in this way. The number of paths from 0 to n to n, which never go below y equal x, is this number. Okay, here total number paths from here to 0 to n to n. Good paths and bad paths, and addition of those two should be 2 and choose n. A bad path always touches y is equal to x minus 1, and so let's say P is the first point touching y equal x minus 1. Then there is a bijection from bad path to path from 1 minus 1 to n. So the number of bad paths can be found as 2n choose n minus 1. Then gn good then good paths can be found. The subtract is bad paths from the all the possible passes, which gives us this number, which is 1 over n plus 1 times 2 and choose n, which was what we are looking for. Here's a Catalan number page on in UCLA, and this has all the possible information that you can take a look. So I expect you can discuss in iCampus Q&A with this interesting number, and then pseudo Catalan numbers also can be defined. And the next thing is a Fibonacci number, which is an optional, and there are lots of things that we can talk on Fibonacci numbers, as you know. And I have made some informations web page of Fibonacci numbers already, and there are some of my explanation of Fibonacci number in the matrix approaches, and also Excel simulations that we did in math modeling class. And yeah, this Excel file also shows this Fibonacci sequence, and there are equalities which comes from the Fibonacci sequence. So I will write down as a property of Fibonacci, which has these many interesting equalities. And this is optional. So these are exercises that you're supposed to do. I expect the team one will do these homeworks. Okay, I think that's the end of week 9. If you have any question, then make it in iCampus. If not, just solve these problems and then share it. Questions?